Okay, welcome to our structural modeling project video conference for July 2017. And we have a few new items to talk about structurally, I guess, this month. First of all, we have put together a new website. Now, this new website is kind of a pre-alpha stage that we talked about here, but one of the purposes of the new website is to organize the material that we have on GitHub and organize the material that we have on ResearchGate in a different way so that it's easier to find. And so what I've done so far with this website, besides set it up, is to put all of the 10 technical reports that have been generated by Systems Concepts, Mary and I there, so that they're easier to find. I know that on ResearchGate, when I try to go through and try to find my technical reports, they were kind of scattered throughout the indexing that's done by ResearchGate. So just an example here of what the concept systems.us looks like. I'll bring that up and kind of walk through that for a minute. Let's see, so I need to share a different screen here. Screen share. And this is a new application window. All right, so this is basically what the new Concept Systems website looks like, the interface. And what we have is essentially broken it into 4 areas. One, I have a link to the GitHub, which has all the code, ResearchGate, which has all the papers, and then papers and presentations, and of course there are papers and presentations. They really only GitHub and ResearchGate, those are active links. They take you to the research, the papers. Basically, I've broken this into research, the technical reports, conference papers, journal, and working. Then we go to the reports, and we get down here and you can see that this basically then has a list of all 10 of these technical reports. Click on the link and it will take you to the ResearchGate version of the paper. So we'll be working on this. As I said, it's kind of pre-alpha, but I put it out there just to kind of give people a heads up that we're doing this, and it'll help, it'll help organize the access to the work. Okay, and of course up here at the top, then this link just takes you back to the front, and then this link takes you to our old site. Our old site we're going to leave for historical purposes, but over a period of time we'll be moving everything over to this newer site. So let's see, okay. Now I need to go ahead and look at this again and change my screen share back here to an application window. All right. So just went through and looked at the new pre-alpha website that we're starting. As I said, we'll be moving and organizing our material differently on this site as we go forward. And then the July technical report, kind of step back, brought it up to a little higher level, look at some of the, an overview of kind of the work that we've done. And we have a little bit more to do at that level next month, and then we'll start making a connection between the global and local relationship attributes and to the algorithms for the software after that. So that's the plan. We'll see how it goes. And looking at the task of overall looking at all this information and starting to map it together, it became clear to me that There was quite a bit of it there, and it's not that easy to access, so that's was the impetus to create the new website with the new organization. So I'll give you another way to start looking at things. So, are there any questions so far? All right, so then we'll go ahead and kind of walk through the latest technical report briefly, and then go on to discussion. All right, so we should have the new technical report up. What we've done in this overview project is bring a number of aspects together that are kind of fundamental in my background context when I'm thinking about the work and when I'm doing the work. But when we're focused on specific aspects, it's not clear to me that everyone has the same context. So this is an idea, this is an exercise in trying to look at a little higher level of context and make some more connections that will allow us to have a better understanding of what's going on. So, of course, there are the standard definitions that we put in. We've added a new definition, a couple new definitions for order, partial order, and degenerative structural thread. And a degenerative structural thread just basically is when you're going through an analysis and you're looking at different components, you actually have just a single object in your output from your analysis. And so it really takes two objects to have a relationship between. So a single object is no other object to support a relationship connection. So that's a degenerative type of structural thread. This is these concepts are being developed, out of the work we're doing with the graphic analysis. We have there's a couple other aspects that we'll probably add definitions as we go forward, but for right now, this is where we are. So the general context for system, for structural modeling and systems analysis, we like to look at Weinberg's view of types of systems. And this is a very convenient or interesting view set for me for systems and their system types, where we start at the origin, and on the x-axis, as we go to the right, complexity increases. As we at origin, and as we go up the y-axis, randomness increases. Of course, in the close to the origin, we have organized simplicity or machines, and we can. These types of systems are readily addressed using typical systems analysis techniques. But as we move further away from the origin, then we move into organized complexity. And these systems are too complex for analysis and too organized for statistics. I think this is a range of where we have most all of our complex social systems fall into this area in some way. And then once you go far enough up the y-axis and have enough objects that you're able to actually use the law of large numbers and create aggregates, then you can use statistical analysis. And there's a lot of very powerful tools in the unorganized complexity area, in the second area here. And there's also many powerful tools in the first area down here with organized simplicity. So it appears to me that structural modeling is being the first step in addressing an unknown or undefined system, starts to create structure. And there's a couple of just general comments about that structure. If you have something that's completely unorganized, but has some structure, so as will be here in area 3, organized complexity. So then what we're able to do is, one, if we apply our techniques of structural modeling, create a structure, and then we find some type of structural component in this area. So the question is then is, what do we do with it, right? Some cases, I believe that the structure that we find in organized complexity areas, then given that structure, that structural component can be addressed using techniques from organized simplicity or machines. So once we have the structure, we can take techniques, analytical techniques that we've developed down in area 1 and apply that to the structure that we find in area 3. And further though, is also that once we have a structure identified in area 3, there's some components that can also be analyzed using techniques from the unorganized complexity or in the statistics area. So step 1, structural modeling, we define a structure, and then once we do that, then we're able to have access to tools, methods, and processes that are applied in these other areas. So it's going to be kind of a general organizing approach I'm going to use. And then this particular organizing approach, I think we'll be able to match to a set of software approaches and a set of software methods. So it's just kind of the reason for using this approach, and I'm going to use it to start organizing some more detailed methods later on. So in the problem solution types, this kind of emphasizes, this chart here kind of emphasizes what I've just said about simplicity and complexity. But if we have simple problems, and they have very low complexity, essentially the problem space is well defined, and we know what the solution space is. The solution space is closed. So these are simple analytical techniques that we can use here. The only job that needs to happen in this first level here, where it's well defined and closed, is determine, let's say, the values of the variables, or what specific objects are necessary to address to solve the problem. So as things become more complex, then they become more uncertain, and that uncertainty creates complexity. So down at the bottom, we look here, we have a situation where it's ill-defined. We have an ill-defined problem space, and we have an open solution space. So in that case, then we apply models for an ill-defined problem space. So then structural modeling would be applied in this model area here to create a well-defined problem space. Now, in this particular area, in this specific instance, you could apply different, multiple models, multiple structural modeling approaches to the ill-defined problem and create a set of well-defined problems. But don't mean to imply that there's only one model here. There may be multiple. But what happens is we use modeling to decrease the uncertainty so we can start applying some of our techniques. In the solution space, it's the same way. The solution space we model, and I believe structural modeling can be used here as well, to create a closed space. And again, this is not just one model. There could be multiple models here that could be used. So then that we can basically apply our problem solution approaches and have well-defined problems that we can match to closed solutions. And essentially what happens here is once we do this, then we go all the way back up here to where we actually have well-defined and closed, so that this modeling process decreases the complexity. You can see we go back up the scale, things become less and less complex. So this is, again, another approach and another type of concept that's familiar, that I have in my understanding and in my context when I'm working with the details of the software and the details of the analysis. And I think it's important that we start writing these things down now and talking about them to make sure that other people agree that it makes sense or it doesn't make sense and it needs to change. Okay, so I need to find the right screen. Here we go. And of course, then we go from problem solution types to language types. And these are, again, the 3 language types that were put together by Warfield and discussed by Warfield, which are the mathematics, the formal language, and structured graphics, can be formal or informal. You have structured graphics that are generated by mathematics, and you can have structured graphics that are like sketches of UML or other types of well-known processes that are informal but still convey information. You can have prose, which are formal, like attempt to English and other types of executable English formats, or prose that are informal, like our normal type of human speech, where most all semantics and meaning are associated with the context of the language exchange. So these 3 language types, of course, can, for any specific subject, can be put together in multiple different ways. You can have a subject that you use mathematics, structured graphics, and prose to talk about, to communicate about. And each of these language types has advantages and disadvantages. What we need to do, I believe, in structural modeling and in the type of complexity reduction area that we're working with is to be able to find out which of these model types fits our audience. And if you're working with a very large audience, that can be problematic. And I also believe that there's some areas here, especially in the mathematics and formal structural graphics areas, where we can address some of these complexity issues and some of the uncertainty through analysis. An example there would be the work that was done by the folks at on the software-defined radio area. The fellow that was the chief architect on that was a software engineer and also a hardware engineer. He had multiple degrees in engineering, and he had a staff of software engineers. He had a staff of hardware engineers and also systems engineers that basically did the integration. And he himself worked both with UML and activity diagrams and IDEF zeros and IDEF type of diagrams. And he did that for a couple of reasons. I think many of them were legacy reasons, that he was bringing in material from software that had that had UML. He was bringing in material he knew about from hardware that had IDEF, and that was just these basically bringing them together. So he then took and encoded the same problem, the same sequential type of process into both of these languages. And what he found, working with his software guys, is they really understood the activity diagrams well. The hardware guys really understood the IDEFs well, but neither group understood them both very well. And so that kind of triggered in his mind that maybe people self-select and go into different areas because they think differently about these fundamental issues. He went on and did some research in psychology and so forth, and found that there's some strong evidence that that's actually the case. And his point about the idea of everybody saying, well, yeah, everybody has to learn UML, or everybody has to learn SML, or everybody has to learn IDEF0. These are formal transforms. We can mathematically make them isomorphic just by using software. So what we should really do is have some kind of simple psychological or perception test or cognition test that we apply to the audience, the people who are going to actually use the language, and determine which aspects of this language do they understand, which form do they understand the best, and then deliver that form to them, because we can do that automatically. And if we say, well, no, we're going to require that everybody, in our audience understand like SML or UML, or everybody understand IDEF0, then you have more of a social political fight where people really don't understand, creates much more uncertainty. And I think that given the level of technology that we have today, that probably a complexity reduction technique pathway lies through the path of working with psychologists and working with cognitive scientists to be able to have some simple tests, working with people to figure out what they understand, and then present the information to them in a format they understand. So that's, I think, a key area where systems science and systems engineering can make some strong contributions. We may not be able to, do all of it, but I think we can outline the problems, we can outline the information and the evidence for that. And I think it would be a really good area actually for testing. I don't know anybody that's doing this, but I think it's something that should be done. Okay, so that's our language types. And then, of course, to work with our isomorphic transforms and that were and the three language types of Warfield kind of generated, talked about, and demonstrated how you use them. We developed the abstract relation type. So the abstract relation type is really patterned after the computer science idea of an abstract data type. But in this particular case, we're not focused on the data. We're focused on the relation, and the relation that actually is the structuring system relation. And so we just create a format where we have formal prose, informal prose, graphics, formal, informal, and mathematics. And what we want to do within the abstract relation type is basically present isomorphic information so that the formal prose, the mathematics, and the formal graphics will all represent the same thing. If you use informal graphics and informal prose, there will be some deviation because of the informality. So that's the idea behind art, and putting that together to communicate system structure. All right, so we've gone through, we've looked at the abstract language types, and then the model exchange isomorphism as logical properties. I think this is very, to me anyway, a very interesting aspect of fleshing out Warfield's work. Warfield didn't go through and list all these combinations of logical properties. He listed some of them, but he didn't list them all. And so in many cases in reading his material and going through and looking at it, there's some uncertainty. You say, well, does it mean this or does it mean that? I mean, how do we know what the real purpose is here? What's the real meaning? So to eliminate that uncertainty, we put together the augmented model exchange isomorphism, which is based on Warfield's model exchange isomorphism, and added the prose component. In this prose component, we require that you have one property from each of the logical groups. One from reflectivity, one from symmetry, and one from transitivity. And then that creates a topology of these groups, these logical groups, that allows us to now have a more complete topology of logical combinations. And then we can start looking at those, and we've got these 27 buckets that we're actually putting things in, and see what is the same and what's different. So that is, we've been using this as a way of analyzing and looking for characteristics in system structuring approaches. One of the things that we have, the system structuring approaches, one of the things that we have found is that for system structure, symmetry appears to be the leading or the controlling system structuring relationship because it involves two individuals. Reflectivity is one individual, so it's really not going to impact the system structure. And transitivity involves three or more individuals, but transitivity, we view that it really is riding on top of symmetry. And transitivity is being a combination of a number of symmetric interactions. So that's another key point in reducing uncertainty by creating a complete topology of these 27 group combinations. Then we went through to general systems theory from Boulding. And of course, general systems theory basically is, was presented as an abstract model building technique that is more general than mathematics. No, it's more general than the specifics, than the specific disciplines, but it's more specific than mathematics. So it lies between mathematics and the specific theories of disciplines. And what we've done is we've said, okay, essentially we have the mathematics language over here, pure mathematics, or it's the BSM area defined by Warfield. The specialized discipline, of course, is the ISM area defined by Warfield. And then in the general systems theory, this is the SIM area that is defined by Mariano. So that's kind of a one-to-one match there between these areas. And the real key, I think the fundamental key discriminator we need to look at is what is, what right here between pure mathematics and general systems theory, how do you know, what are the primary discriminators that say, oh, I'm in mathematics? nope, I'm not in mathematics anymore. Now I'm over in general systems theory. And the same with specialized disciplines. So, okay, what are the discriminators that say, okay, I'm in a specialized discipline, I'm not in general systems theory anymore? So these are a couple of boundary conditions, I think, that need to be more well defined and talked about. I think they're important for a number of reasons to help categorize and understand certain different behaviors in system structure. So just talked basically about that, the difference in most parts. And this is kind of a brief, high-level first attempt to look at some of the attributes associated with this definition of general systems theory. And one of the things I found interesting about Boulding's work was he talked about meaning. Mathematics really has no meaning because it applies to everything. And so that's a semantic type of argument, because the human beings determine meaning, semantic understanding from context, where mathematics, that's basically determined from formal rules, axioms, and logic. So the content for mathematics is none. GST is a general pattern, and the specialized disciplines are domain-specific patterns that happen in this context, or in this content is domain-specific. Then the context for mathematics is universal, but the GST is constrained to the pattern. So the general systems theory is more constrained than mathematics, focuses on a smaller area, and then of course the specialized discipline, basically their context is constrained to the domain that they're working in. Syntax for mathematics is formal. GST is formal and informal. Same with specialized disciplines. And again, the meaning derived from formal rules. And GST is derived from a system pattern and then determined from the domain context. So haven't had time to actually go back and really look at the definition of general systems theory by Boulding. He's talking about meaning, what things mean. And I think that's a good area to look at, especially in terms of ontologies and the different types of interpreters, like a human interpreter or a machine interpreter. And it's, anyway, I think there's some very interesting and fundamental aspects to that. We may go into that later on, I'm not sure. And this is basically just the overview of the structural modeling components. As I talked about before, we have the basic structural modeling, which is mathematics, interpretive structural modeling, which is domain experts, and of course the system integration modeling, which is the systems scientist and systems engineer in this particular area. And I think one of the things we can do to help answer the question of what's the difference between pure mathematics and general systems theory is start thinking about what is this translation? What are the transforms between basic structural modeling and BSM and structural integration modeling, or SIM. And it may not be a direct map, but it's a place to start when you start thinking about that. And the same for what's the difference between GST and domain-specific information. And we can start thinking about what's the difference here between SIM and ISM. And those are the types of things I think we'll probably highlight in the future. So the three organizing properties of symmetry, as I talked about before. We some interesting just ideas here at a very high level on the three system structural types. We have asymmetry right here creates a hierarchy. Symmetry creates a network, and then non-symmetric combined hierarchy and network basically creates a hierarchy of networks. And we have different ways and different applications that we do here. But mostly what we do is try to take, if we have a non-symmetric situation, we try to take it apart and deal with the hierarchy with one set of tools and the network with a different set of tools. As we talked about in Weinberg's three areas, when we go in and we find a structure for a system, if we go through and we find it's hierarchical, then we can probably apply some analytical techniques from the simple machine area, because you have a highly constrained type of structure. And if you have go in and do the analysis and do structure modeling, find out you have a network, then there's aspects of the network that you could explore using statistical methods. And if you find you have a combination, then you would want to break it apart to a hierarchy, use some methods to analyze the hierarchy, and then use methods to analyze the nodes in the hierarchy that are networked. So that's kind of a decomposition type of approach to look at this. We've, in the past couple of years, we've been focusing mostly on the hierarchy piece. Before that, focused on the statistical analysis and the network piece quite heavily. So the methods and techniques and code for the network component have been developed and used before. We just haven't been looking at that recently. And so as we go forward, and as it's developing more, I believe that this will kind of come together either in some high-level processes and some high-level approaches to engage complexity. Then we looked at the four documented relationships, the heavier than, same category as, and the is of higher priority than from the handbook, and then north of, which is from the work that Mary and I did a few years ago. And so what we're starting to do now is looking at these and starting to categorize them as either being global or local, and whether they're then objective or subjective. And of course, then we pair that with the symmetry component that's correctly associated with that relationship. So now we're starting to have these more discriminating characteristics, more discriminating attributes, and defining those in a way that we can now start to further categorize and group types of natural language system structuring relationships. And we then have an idea of what types of mathematical tools we should apply. So mathematical tools that we use with the asymmetric component will be a little different than the ones we use with the symmetric component. The processes, the group processes, and the way that we work with the people in the group are going to be a little different if we have an objective type or a subjective type. It seems like if you have a subjective type of attribute in your relationship, it's going to need to be a little bit more work done with a group of individuals to try to make sure that everyone has a common understanding of what's going on. And we just walk through these and talk about them and start to match the attributes to the outcome of the structural threads of the graph. And so here we say, basically we have a single thread, single structural thread object for the is heavier than, which is global and objective. And then we have a single structural thread for spatial position, which again is objective, global. But unlike the is heavier than, now we allow two cities to be at the same level or at the same latitude. And really what we're doing here is we're not so much ordering the cities directly in the set, we're actually ordering the latitude. And so the latitude that has two cities, we say that we're, the latitude is north of. And we don't, of course the cities are too, but that's kind of a natural language semantics. If you only have one city at each level, then it's a one-to-one relationship and there's no problem. If you have more elements, then that needs to be clarified and probably worked out a little bit better with people that are performing the ISM activity. And then for the same category as, basically again it's global because we have global concepts or patterns for each one of those categories. But it's symmetric. We have a symmetric type of relationship for the equivalence. And we have a single thread per category. So this is a global relationship that is has a symmetric component, and it generates one thread per concept. So this way, we're just laying down some of the fundamental concepts and ideas about structuring relationships that we think would be useful and are going to help guide our selection of tooling and techniques and methods when we start engaging a group of people to structure these systems. And this is the priority, the higher priority then. So in this case, it's objective. It's a subjective type of activity, and that needs to be worked out. And then the differences between whether they're the same or whether they're different, how much differences have to be, or how for the objective to be at a higher priority. That is also an important thing that needs to be addressed. And if the goal of this whole activity is to prioritize objects, if we left them all at the same level, then we would basically have failed in that activity because we didn't find a discriminator. So in this particular case, where we have three objectives at one level, might need to try to be able to come up with some other type of discriminator that allows you to separate them. So the best or the highest value outcome is if you have all 8 separate with no objectives at the same level. But so that's the idea. You need to work with a group to figure out, one, what are the characteristics of the global prioritization, what are the parameters, what are the discriminators, how are we going to tell a difference, and then when you're working with a group, after that has been determined, then you need to observe the outcome, and if it's not working, if it's really, the outcome is the discriminators you're using are not, don't give you enough separation power, then you might need to go back and try something else. So, in summary and conclusions are just basically that we're starting to align the structural modeling techniques with GST, using the abstract relation types and AMEI to help further develop and define structuring relationship characteristics and attributes. And the reason for doing that is to support specific types of software processes and application processes within a group. So that is basically the overview of our presentation for this month. Are there any questions?
Well, yes. Thank you very much for that.
Peter, okay.
Good summary, which I think is very helpful. I wonder, you mentioned really three areas for research. One is the sort of psychology and cognitive receptivity. Another was matching approaches to, or computer or software approaches to problem type. And I forgot what the third one was that you had. So that's a question.
Okay, the third area for research.
Yeah.
So basically, we have the human cognitive perception. How can we deal with that? And the next one is to start identifying the characteristics of our natural language. So we're using natural language structuring relationships, and now we are assigning specific characteristics and attributes to those, and then we want to match from those attributes to the mathematics. So we need to make some distinctions within that group. For example, in Boulding's GST definition, when you're talking about mathematics, really that's mathematics only, right? The mathematics actually is in GST, and mathematics is also used in the domain specific.
Mm-hmm.
So it seems that the discriminators for those boundary lines are not associated with mathematics, but they're associated with the translation from natural language to mathematics.
Mm-hmm.
And that's where the SIM area is. Mm-hmm. So we're saying, okay, how is this meaning encoded within a domain-specific group? That's in all the specific domains. And then when we move to GST, we say, how now is this information encoded in a general way? That makes sense?
Yeah, no, absolutely. I am interested in, well, all of that, particularly though the human and cognitive pieces, at least to start. And we, the College of Exploration, does have access to some tools to make an appreciation of various characteristics. And I wonder, with this group online now, how willing you are to actually participate. Perhaps if I sent you the link to this appreciation, whether you would be willing to, to participate in that, if we just to get a sense of how the two instruments that I have might apply, just as a first instance to bring some kind of discourse to that approach. Would you guys be willing to do that?
Sure.
Okay.
As long as it doesn't ask for my social security number, my birth date, or my mother's maiden name.
No, you don't need to know any of that. You can anonymize it if you want, but it could be helpful too, because that would be good. Thank you.
Say more about what you're talking about, Peter.
Well, it's I'll send you some links to the website, but essentially they are two instruments. One is called a linked personality appreciation, and it addresses a number of factors: learning type, the way you develop, the way you deal with conflict, the kind of personal situations how you like to work, what kind of characteristics you would bring to a team. That kind of thing. And then the other one is a measure of how you match to a model of complexity, and how your capacities to think in increasing levels of abstraction match this particular model. So as I saw in those diagrams there, the kind of different ways of approaching increasing complexity by structuring the problem situation. These would help us to add to our language of how natural language matches to the structuring at whatever level, and give us perhaps some insights into how one would approach this. It's particularly these kind of questions are of interest to the National Science Foundation. So I do have the thought that perhaps it might be the basis for a proposal of some kind, if that's of interest to this group to think about.
Are these are questionnaires?
Yeah, essentially.
Okay. You say instruments, it's very education evaluation terminology specific. Yeah. Okay.
Well, I mean, they're more, I'll send you some references to all of you. You can read the background on all of it, okay?
Well, yeah, I just wanted to make clear that it's not a big commitment. I don't think it's a big commitment of time to fill out a question.
They're each about 45 minutes.
Okay.
So what I'll do is I will send, okay, I got a couple of action items here. One is to do the Ireland note to you, Peter, and the fellow in Ireland.
Good.
And then the other one I'm going to do is I'm going to go dig up the papers from, I think the fellow's name was Doyle, and that he wrote about this cognitive perception. And at the same conference I was at, there was also some contractors for the NSA which had done some work. And what they were saying was that UML, and they were talking specifically about a government edict that said they had to encode everything in UML. And they were just basically following that, and people were just throwing them out of the building. They weren't going for it. They weren't going to have any of this nonsense.
Right. Well, I think that relates to perhaps another question I had, which is to in the structuring of the relationships of these approaches to different problem types at different complexities. It's how to relate it to the model-based systems engineering approach. And you've just touched on it. Is that for some engineers that means UML for everything. And of course, you run into all kinds of problems about structuring if you're trying to, apply the hammer of UML to every problem or design approach. So some ways to, I think, Janet and Michael and Dwayne and I are working on the system foundations for systems engineering for the CBOC. And so to have some ways to express the importance of being careful about the selection of the tools to match the problem situation would be very helpful. And it makes a big contribution in that direction. Thank you.
Yeah, so basically what these folks did, they had to do something, was they went and they selected Joseph Novak's concept mapping, which is much more human-faced and has human types of names on the links, and people could understand that. And then they worked with that with the people. Then they brought it back, and then they converted it by hand to UML.
I see.
And so one of the key factors there, though, is that the structure of a concept map is not formal.
Right.
I mean, yes, a few rules, but I mean, each one's going to be different. And so there's an ontology that really needs to happen there. And there's a lot of people working on that. But to me, that's kind of the translation. Well, what do we do to go from informal to formal? And what information do we lose? What benefits do we lose? What benefits do we gain? You know, what are the trade-offs in those different languages? If we can automate that, we can use them all. We don't need to force everybody to use the same thing. So the benefit of using a formal language is you can automate the translation.
Yeah, that's great. I mean, as long as you've got your rules of translation are very transparent. I mean, the other point or the question I have, which we don't need to answer today, but the approach that you're taking has a sort of very English language feel to it, and I wonder about, you know, how one would express this to a Chinese audience or to a Japanese audience or an Indian audience or even a Spanish speaking group, where of course the language emerges from a very different cultural sense, and even its expression in characters and idioms and pictograms are very different. And I wonder if there's anybody paying any attention to that in any way.
Well, I'd say that essentially, and I think Kevin probably knows a lot more about this than I do, but they used ISM with the government of Mexico to work with indigenous people who were basically illiterate.
Right.
And so they used the indigenous people are illiterate according to the dominant culture. Let's put it that way.
That's better, yeah.
And so the cultural conflicts in the languages is important. The other thing that's important is that the graphics allowed them to quickly develop their own context-specific language. And so that because you're using mathematics and graphics, if the prose don't match, you can still go back and then work in short-term, short-hop cycles to create a project-specific language that's good enough to get you through.
Okay.
Okay. So we're getting close to the end here.
Yeah, Michael and I do need to run a little bit early, actually, but I wanted to raise the issue of should data be a separate AMEI perspective? It's not really, it doesn't, where does it fall? Especially now that we have machine learning that maybe, to some extent has a culture of data that it might be illiterate in other forms, but it's very data oriented.
Well, that's really good, because I just don't know how to, I guess on one of the other lists I follow, they're working on the idea that information is comprehension times extension. And so they're going through and breaking that all apart. If they achieve some consensus on that, I believe that we can make subcomponents. Mm-hmm. But there's the idea of comprehension includes meaning, which also is in GST, which is again a little context specific. But it's a good point, Janet.
Yeah, maybe we can talk about it some more in 2 weeks if we're going to meet again. If Kevin, are you going to be available?
Yeah, I'll be available.
Okay, good. And
all right.
So we have to run. Excellent summary. Talk to you later. Bye-bye.
Bye-bye. All right, well, that kind of concludes our July video conference, and we'll convene in 2 weeks. Take care, have fun.
Thank you very much indeed. That was really good. Thank you.
Okay.